Let's do a thermal equilibrium problem. We got a 0.3 kilogram slug of lead at 150 degrees Celsius. It's placed in an insulated container that holds 0.6 kilograms of water, and the water is at 5 degrees Celsius. What is the final temperature after thermal equilibrium is reached, and how much heat left the lead and how much heat entered the water? So I kind of got it started. Here's the water, right in here. We lower this lead in it and seal the top so that no heat can get in or out of this. That's an insulated container. And so we said the mass of the lead is 0.3 kilograms. It's at 150 degrees Celsius. And then the water, the mass of the water in there is 0.600 kilograms. And its initial temperature is 5 degrees Celsius. Surprisingly, it's not going to be very warm. I don't know if you've done it yet. It's not going to be a very high temperature. Now, a couple things you have to look up. You have to look on page 279, and if you do, you will find that the specific heat of lead is, what is it?
130? Yeah, 130 joules per kilogram per Celsius.
Joules per kilogram. I think it says kelvins in there, doesn't it? Now, here's one thing. It doesn't matter if you're using kelvins or degrees Celsius. You can use either one. So I'm going to use degrees Celsius for this problem. And then you have to look at the specific heat for liquid water, and it's a pretty big number. What was it?
4,180 joules per kilogram times.
Okay. And so now we've got everything we need to solve this problem. What do we want to find? For A, we want to find the final temperature. For B, we want the heat for the lead. And for C, we want the heat for the water. Okay, makes sense? Okay, so if you're watching at home, pause it and try it yourself. All right, let's solve this. Well, we derived a final temperature equation, and usually I like to start from basic physical principles and then derive the equation, but it's so cumbersome to do that every single time that I just said forget it, and we derived this. And so if you look at one of the lectures, the lecture on thermal equilibrium, you say, okay, the final temperature for something like this is going to be MLCL for the lead times the initial temperature of the L plus MWCW, the initial temperature of the W, that's the water, divided by the mass of the lead, the specific heat of the lead, plus the mass of the water times the specific heat of the water. And this is a pain. Nothing cancels out in this problem. Sorry. That's the way it goes. So the final temperature is, now we got to put all this in, for the lead, 0.3 kilograms. Specific heat of the lead, 130 joules per kilogram degrees Celsius. The initial temperature of the lead, 150 degrees Celsius. Plus the water, 0.6 kilograms times 4,180. Look how much bigger, look how much more energy it takes to change the temperature of water than lead. That's what's amazing about water. Water can just take the heat. And then the initial temperature of the water was 5 degrees. And then you just do this, 0.3 kilograms times 130 joules per kilogram degrees Celsius plus 0.6 kilograms times 4,180 joules per kilogram degree Celsius. And so look at this. Joule, kilogram, that's in every term. The units for the specific heat are in every term, so you can just cancel them out. And kilograms is in every term, so you can just cancel it out. Now everything in the denominator has been canceled out. That's okay. But in the numerator we have degrees Celsius left over, and that's what we want. So the units make sense. Now we have to do this on a calculator, and you need your calculator skills to be highly refined. So now what I sometimes do is I'll do the numerator and then write it down, and then the denominator and write it down, and then, because it's too easy to make lots of mistakes. Now I used to use a Hewlett-Packard calculator with reverse Polish logic, and it would cut through something like this easily, but I have one of these TIs. And so anyway, 0.3 times 130 times 150 equals, and then I'm going to go plus, and I'm going to put in parentheses, 0.6 times 4180 times 5 equals, now for the numerator I got 1.839 times 10 to the 4. Is that right? Yeah. Degrees Celsius. Now I got to divide that by the numerator. Let's just do 0.3 times 130 plus 0.6 times and did you get 2,547 on the bottom?
Yeah.
So now I just divide the numerator by that. So I go, let me just do this. It's 1.839 times 10 to the 4 divided by 2.547 times 10 to the 3 equals, and look, I get a ridiculously small number, 7.22 degrees Celsius. You agree with that? Isn't that kind of surprising? I mean, you'd say, wait, look at this. The lead, well, there's less lead than water, but only there's, it's only half the mass of the water. But look how much hotter it is, 150 degrees. You put that in the water, you think, oh, okay, it's going to warm the water up a lot. But it didn't. And that's because of this thing right here. Specific heat capacity of water is very, very big. That's actually a good thing. Okay, so that's our answer for A. Now for part B, well, Q equals MC delta T. So the mass, and for B it's lead, right? Yeah, we want the heat from the lead. So that's going to be 0.3 kilograms. And it's going to be 130 joules per kilogram degrees Celsius. And the change in temperature, it's T final minus T initial. Well, T final is 7.22 degrees Celsius. Minus T initial, well, the initial temperature, let me zoom in. People can see it better. 7.22 degrees Celsius initial, now the final, the initial temperature was 150. And so you plug that in, and that's the heat from the lead. 0.3 times 130 times 7.22 minus 150, close parentheses, equals negative 5,000 5,570 if I round it off joules. That's right. The Celsius cancels, the kilograms cancel, leaving joules. And what's negative? What does that mean? Yeah, it lost heat. It lost heat. Now let's do the water. Well, if you just want to sledgehammer it, Q equals MC delta T. So you got 0.60 kilograms of water. You got 4,180 joules per kilogram degrees Celsius. And you had a final temperature of 7.22 degrees Celsius minus the initial temperature of 5 degrees Celsius. So Q for the water, let's see, 0.6 times 4180 times parentheses 7.22 minus 5. Oh, what do you know? I got positive 5,570 joules. Well, look at that. It's the same number. I guess the heat that left the lead is equal to the heat that was gained by the water. If it comes out negative, that means we dropped in temperature, which means we released heat. If delta T is positive, that means it got warmer. That means it had to absorb heat. It gained heat or gained thermal energy. And that's how much thermal energy it gained. It makes sense. Does it make sense? Okay, let's zoom out. Look at the whole bloody thing here. Kind of small, but it's okay. So there's the whole problem. And there will be a problem on the test very similar to this one. So, any questions? Okay, that is all.